The van der Pol equation, qualitative and numerical analysis. We begin with the van der Pol equation's deduction, then we'll state some theorems that will be used in qualitative analysis and make some analytical approximations, and at the end we'll make some numerical analysis. So the deduction utilizes this oscillator circuit. We applied the Kirchhoff's current law, and using each current through each component, we can derive the normalized van der Pol equation. We can write this equation as a Leonard system as expressed in this page. Before getting into the qualitative theory, it is important to make some definitions. First, we considered this nonlinear system with an equilibrium point XO. And an equilibrium point is said to be locally stable in sense of Lyapunov if in the neighborhood of this point all trajectories stay close to this point. An equilibrium point is said to be asymptotically stable if all trajectories tend to this point as time approaches infinity. And the omega limit set is the set of all of the accumulation points with a sequence tk going to infinity, and the alpha limit set is defined the same way but with tk going to minus infinity. The Lyapunov's indirect method considers the linearization of a system in order to study its local stability. So if the linearization exists, its stability implies local stability for the original nonlinear system, and an equation can be linearized by the Jacobian matrix. If all if the real part of the eigenvalues of this Jacobian matrix is positive, the equilibrium point is locally unstable. If the real part of the eigenvalues is negative, the equilibrium point is locally stable, and for eigenvalues equal to 0, the linear approximation is not sufficient to determine the equilibrium state of a system, but this case does not occur studying the van der Pol equation. Studying a nonlinear system, it is important to check if the omega limit set has periodic solutions, which are the limit cycle, and they can be classified as asymptotically stable if all neighboring trajectories approach the limit cycle as time approaches infinity, unstable if all neighboring trajectories approach the limit cycle as time approaches minus infinity, and semi-stable if one trajectory approaches the limit cycle as time approaches infinity and the other as time approaches minus infinity. The Poincaré-Bendixsen's theorem considers an open set, subset of the two-dimensional space, and a vector field of class C1 with finite number of equilibrium points. So if P is so that the positive trajectory applied to this point is contained in a compact set of this open set, then if the omega limit set contains only equilibrium point, it is a single equilibrium point. If the omega limit set contains only regular points, then it consists of a single closed trajectory, and if the omega limit set consists of equilibrium points and regular trajectories, then all trajectories tend to equilibrium point as time tend to infinity and to minus infinity. The Lyapunov's direct method is the generalization of an energy function, and the idea is to find candidates to Lyapunov function and then analyze the behavior. A Lyapunov function considers a vector field and an equilibrium point with A being a neighborhood of this equilibrium point, and V is a Lyapunov function if applied to the equilibrium point is equal to 0 and positive in a neighborhood of this point, and if it is a non-increasing function. The Lyapunov stability theorem says that if the Lyapunov function is only non-increasing, then the equilibrium point is stable, and if this function is strictly decreasing, the equilibrium point is asymptotically stable. The qualitative study, here we have our system, our van der Pol system, we can see that the only equilibrium point is the origin, so the Jacobian matrix is given by this matrix. After calculating its determinant, its eigenvalue, they are given by this relation. So for epsilon equal to for negative epsilon, the real part of the eigenvalues is negative, so the origin is locally stable. For positive epsilon, the real part of the eigenvalue is positive, so the origin is locally unstable. And for epsilon equal to 0, the van der Pol equation reduces to a linear equation with solutions of this cosine form, where the amplitude, where A is the amplitude and phi is a constant of phase, and they are both determined only by the initial conditions. In order to apply the Poincare-Bendixsen's theorem, it is important to know the behavior of the derivatives of the system, both in polar and in Cartesian coordinates. So we can write this system as in polar coordinates, and here we'll analyze this first equation, which is the first time derivative of the radius. And here we can see that for negative epsilon, in the neighborhood of the origin, the radius decreases, so there is an attracting term to the origin, and outside this neighborhood of the origin, the radius increases. For positive epsilon in the neighborhood of the origin, the radius increases, so there's a repelling term around the origin, and outside this neighborhood, the radius decreases. Now the analysis in the Cartesian coordinates. Here we call this part of the function an f of x, represented by this blue curve, these blue curves. If a point is above this curve, the x coordinate increases. If it is below, the x coordinate decreases. And for y equal to f of x, x is constant. Whereas if a point is of positive x, the y coordinate decreases. If x is negative, y increases. And for x equal to 0, y is constant. So in this after applying the Poincare-Bendixsen's theorem, we saw that for negative epsilon, all trajectories with initial conditions in a neighborhood of the origin tend to this point. So the origin is an omega limit point, which yields that the omega limit set consists of a single equilibrium point. For positive epsilon, all trajectories with initial conditions inside a neighborhood of the origin go outwards the origin, so the omega limit set contains only regular points, and therefore it consists of a single closed trajectory, which is the limit cycle. We applied the variable gradient, the method of the variable gradient, in order to find a Lyapunov candidate given by equation 9. If we let C1 and C4 positive, the first condition of the definition of Lyapunov function is easily satisfied, because applied to the origin it is equal to 0, and out in a neighborhood of the origin it is positive. And if we let C1 and C4 to be equal, this is the first time derivative of the Lyapunov function. Now we can analyze this function, and we see that for a domain defined this way, for negative epsilon, the Lyapunov function is strictly decreasing, so the origin is asymptotically stable. Whereas for positive epsilon, the Lyapunov function decreases outside this domain and increases inside this domain D. So since there exists a limit cycle, this behavior shows that the omega limits, the limit cycle is asymptotically stable. Some approximations. First, we consider weak nonlinear oscillations. So this is the approximate solutions, where we can say that A is a slow varying function with respect to time, and using the van der Waals system in polar coordinates, we can write, after some calculations, an expression for A of t. Then we substitute on the general solution for small values of epsilon, and the c is a constant of integration, and we see that for positive epsilon, as time approaches infinity, this denominator tend to 1. So the amplitude in the steady state tend to 2, the amplitude of this oscillation. But this equation does not hold for sufficiently large values of epsilon, but it is still possible to study the system's behavior over time. We let this change of variables and call this function a g of x. So if y1 minus g of x is of order sufficiently large, as we approach, as we tend epsilon to infinity, x also tend to infinity, and y1 tend to 0. But if y1 minus g of x is of order 1 over epsilon, x does not increase, does not tend to infinity. And this is what we approach here in order to sketch these trajectories. We chose an initial point to be sufficiently apart from g of x, and initially the trajectory is fast and almost horizontal. After the trajectory reaches g of x, it becomes the trajectory becomes slow, and then it reaches a certain point where the trajectory becomes fast, then another slow trajectory, another fast trajectory, and this slow trajectory followed by a fast trajectory is what gives this name, the name of this oscillation, the relaxation oscillation. So here we can see that a limit cycle forming. We can easily calculate using g of x those points A, B, C, and D, and we can use the idea of relaxation oscillation in order to estimate the period of these oscillations. So we can neglect the time that it takes from point A to point C and point D to point A, because the trajectories are fast. These trajectories are fast, and we can integrate the time from A to B, and this is half of the period. This is expressed here in this equation, and using the system, using our system, we can change this integral to an integral over x, because we know points xa and xb. So after some calculations, we reach the period of this relation, which is the period of the oscillations, with an error of order 1 over epsilon. This is just a sketch of this relaxation oscillation behavior over time. The numerical study is used in order to illustrate graphically the analysis made thus far, and we used Octave and Python in order to numerically integrate. The phase portrait for negative epsilon, the phase portrait for positive epsilon, for epsilon equal to 0, temporal behavior, the basings of these two basings of attraction, one estimated using the Lyapunov function and another one using obtained empirically using Octave. These are the references used in this presentation, and thank you so much for watching.